Hello and welcome to a presentation from LECO Corporation, a leading manufacturer of time-of-flight mass spectrometers, specifically GCMS systems. I'm John Hayes, the Separation Science Product Manager at LECO, and today I'm excited to share a brief history of how almost 3 decades of LECO mass spec innovations have led us to the present, and also to discuss what the future holds for time-of-flight mass spectrometers. Later in this presentation, I'll welcome members of our research and development team and applications team to present to you firsthand some of the exciting developments at LECO and what these innovations mean for your GCMS workflows. I want to start by highlighting some of the interesting MS history that's gone on in Michigan, the state where LECO is headquartered. It was in Midland, Michigan at Dow Chemical where some of the first experiments with coupling mass spectrometers with GC occurred in the 1950s. The primary limitation of MS developments at the time was computational power, no surprises there. But if we flash forward to the 1990s, yet another GCMS innovation would occur in Michigan, just down the road in Lansing. At Meridian Technologies, a small research and development group started by Michigan State University professors, physicist Vyacheslav Arteyev and computer programmer Kevin McNitt developed the FCD, or Fast Chromatography Detector, a GC TOF MS that took full advantage of the fastest computer processing chips at the time. The ultra-fast acquisition speeds of the TOF permitted greatly accelerated separation and detection in complex chemical mixtures. Here's where LECO, headquartered in St. Joseph, Michigan, got involved. In 1995, they hired these 2 GCMS upstarts to continue development of the GC TOF MS with the expanded resources available at LECO. LECO had been designing and manufacturing scientific instruments since 1936, with a focus on high-speed analyzers for the metals industry. Accordingly, the lightning-fast GC TOF MS fit right in, and was quickly commercialized into the first GC TOF MS available to the general marketplace, the Pegasus, introduced in 1996. A decade of research and development led to several iterative improvements in the form of GC by GC and high-throughput models, many of which are still in operation today. The focus of today's presentations will be on our 2 current GCMS models and their history and future of innovations, starting with the HRT, or High-Resolution TOF. First introduced in 2011, the HRT delivers selectable mass resolution of 25,000 or 50,000, even at acquisition rates of up to 200 Hz. Since its introduction, it has been the beneficiary of many design innovations, some of which we'll highlight today. The Pegasus BT, or benchtop model, replaced the original Pegasus series as LECO's high-sensitivity, nominal resolution instrument. Though the footprint is much smaller, the BT actually delivers huge sensitivity and robustness upgrades over its predecessor. We'll start our discussion of the HRT with its most quintessential innovation, the folded flight path design. Looking at the exterior of the HRT, one might be surprised to learn that the ion flight path can be as long as 40 meters. Longer flight time allows greater separation of ion packets and thus increased resolution. Thus, long flight tubes have always been a part of TOF design. Original designs simply pulsed ions down the flight tube towards the detector, like in this simple 1-meter schematic. Incorporation of reflectrons effectively doubles the ion flight path in the same linear dimension, and so single and multiple reflectron designs have become quite common. In theory, the ion flight path could become incredibly long in even a small linear distance so long as there were sufficient ion reflections between the pulsar and the detector. LECO pushed this concept to the extreme and developed a multi-reflecting time-of-flight analyzer, such that ions are sent back and forth many times between 2 ion mirrors, which act like reflectrons. Focusing electrodes between the 2 ion mirrors keep the ion packets tight, ensuring excellent resolution and sensitivity in spite of the extra-long flight path. You may recall that the HRT has selectable modes for 25,000 and 50,000 resolution. This is thanks to a selectable feature to send pulsed ions back down the flight path for a second time before reaching the detector. The clip on the left demonstrates the ions completing 1 full cycle between the ion mirrors before reaching the detector. The clip on the right shows the same ion packet instead being sent for a second pass through the ion mirrors thanks to the activation of an additional lens. The flight path, and therefore the resolution, are effectively doubled. This can be useful in situations where isobars require additional resolution for distinguishment, or additional power in pulling away key fragments from matrix background is desired. The next key innovation expanded the linear dynamic range and sensitivity of the HRT, encoded frequency pushing, or EFP. The spark for EFP came from considering traditional orthogonal acceleration or pushing strategies in time of flight. The ion beam originates in the source and proceeds through transfer optics, where small portions are pulsed into the flight tube. Traditionally, the pulses occur at such an interval that the flight tube has time to clear all the ions, so that ions from the previous push don't interfere with those from the next one. However, this means that a substantial portion of ions are essentially wasted, and that they don't make it to the detector to produce signal. Low duty cycle, which can be thought of as what fraction of generated ions are ultimately pulsed down the flight tube, is the enemy of good mass spec sensitivity. The LECO research and development team was dissatisfied with the duty cycle available based on the traditional principle of flight path clearing, and so they explored alternative strategies. But the reality remained that pushing more frequently meant ions from one pulse interfered with another. So rather than try and prevent interference, they sought to introduce a unique pattern to the pushes, such that the resulting multiplex spectra had a sort of key embedded therein. Thus, the combined spectra could be decoded into a coherent MS spectra with the key. The benefits of this new pushing strategy are many, the most obvious of which is the increased sensitivity. Consider the traditional pushing strategy, with all the wasted ions between pushes. By comparison, when using EFP, the same ion beam is pushed many times more frequently, thus the wasted ions are far fewer. In practice, this yields about a 10-fold increase in sensitivity. EFP has several bonus benefits beyond just the raw sensitivity increase. The mass accuracy is improved due to the stronger and lower noise decoded signal. The linear dynamic range is extended on the low end. Ordinarily, this comes at the expense of saturation of the high end of the instrument. However, with EFP, the number of ions reaching the detector is not increased for any given peak, so the sensitivity bump is enjoyed across the entire dynamic range without detector or source saturation issues. Lastly, the spectral quality is improved thanks to an effective boost in in-spectrum dynamic range. Low-intensity fragments are retained due to their presence across the multiplex spectrum, while noise fragments that would ordinarily appear in a single spectrum are rejected. Most recently, LECO introduced the multimode source, or MMS, to expand the HRT's capabilities into identifying true unknowns. Beyond traditional electron impact ionization, positive and negative chemical ionization techniques offer unique benefits to GCMS users. They are excellent for extracting molecular ion information, which in tandem with excellent mass accuracy, allows investigators to determine chemical formulae from the mass spectra. But even on high-resolution, accurate mass instruments, their use has been somewhat limited due to some common hindrances, like time wasted on changing out sources, re-evacuating the MS, having to retune the instrument, and so on. The reality was that the current sources were not meeting the needs of non-target and discovery users. If you have a question when operating in EI mode, you want an answer from CI right away, not a day later. The design philosophy for the MMS was to create a single source that optimized both CI and EI. The result required two separate ionization volumes and filament styles, contrary to the single-chamber styles employed in other CI designs. This allowed for the pressure optimization for the respective modes, critical to maximum molecular ion generation in CI mode. The MMS is mounted on a single flange for easy installation, and the number of parts requiring disassembly for cleaning was minimized. EI data from the MMS will be familiar to GCMS users, exhibiting universal ionization and high sensitivity. The spectral matches against traditional databases are consistently excellent, thanks to the absence of ion trapping and resulting space charge effects in the true time-of-flight design. This is critical when attempting to identify unknowns, or to infer structural information from the EI spectra. And with the MMS, collecting CI data is as easy as adding a line to the batch table, providing confirmatory molecular ion and adduct ion information. This is especially critical in situations where EI spectral fingerprints are more ambiguous, like in the example of this chlorinated pesticide below. Soft ionization data from CI is critical to making a high-confidence annotation. Again, the lack of space charge effects and spectral skewing means that in addition to the molecular ion information, isotopic fidelity of any fragment cluster can be assessed for additional confidence. Next, I sat down with Dr. David Alonso from our applications team for some insights into how the HRT is used for forensics, metabolomics, and environmental workflows.
I'm an applications chemist at LECO Corporation, and I've been at LECO for just over 12 years now.
Excellent. Well, a lot of innovation and exciting developments over the past 12 years. Do you have a favorite perhaps, and can you tell us a little bit about how it might have affected your workflow?
Yeah, I really don't have a favorite. I think what makes the instrumentation that LECO produces fantastic is the overall package that includes not only the hardware but the software. And there's many innovations that have been coming out every year for LECO. That includes encoded frequent pushing, which affected the sensitivity, new sources, redesigned mass spectrometers in terms of the optics and so forth. And again, it's the complete package that has made the instrument what it is today.
I see. How about working with the MMS? How has that been?
Yeah, the multimode source is our new CI source, but it has electron ionization, positive and negative chemical ionization capabilities. It's a very nice addition to the high-resolution time-of-flight instrument that allows for seamless transition between the modes without exchanging the source. But more importantly, it complements the package that is the high-resolution TOF instrument, which combining enhanced chromatographic resolution as well as the high-resolving power of the mass analyzer allows you to answer a lot of questions that normally you can't answer. And with the MMS source, you get the capabilities of acquiring, of course, different data, which is complementary to each other and provides additional information for confident annotation of the, in the case of metabolomics, metabolites, or in the case of environmental studies, perhaps pollutants. And this brings to mind a study that we did in metabolomics / environmental, where we were actually looking at human biofluids. And of course, when you look at these samples, they're very complex, and often the compounds of interest are very low trace levels.
I see.
And of course, with the high-resolution TOF and the MMS, or multimode source, we were able to detect compounds that we hadn't seen before. Specifically, the polyaromatic hydrocarbons we've seen before, but trace polychlorinated phenols, polychlorinated biphenyls at very low levels in plasma.
Very exciting.
Yes.
Now we'll move on to the most recent addition to the LECO lineup, the Pegasus BT, or benchtop system. The benchtop has a shorter history of development, but still boasts some exciting mass spec innovations. The Pegasus BT owes its smaller footprint to a simpler design. A single reflectron design serves as the mass analyzer, and there is no orthogonal accelerator for ion introduction. Instead, ion pushes occur directly from the source, thus foregoing the traditional transfer optics required. In fact, the unique ion source required for this configuration provides one of the best benefits of the Pegasus BT. The design requirements to permit in-source ion pushing include an open-style format for ion accumulation without space charge effects, and minimal surface area of the source materials. The result is very little chemical interaction between source and sample, yielding exceptional robustness. So robust, in fact, that there is no need for routine source cleaning, even with the most challenging matrices. Hence, LECO has dubbed the design Stay Clean. I sat down with Dr. Matthew Soik, product leader for the Pegasus BT, for some more insight on ion source development at LECO. For starters, can you just tell us a little bit about your history at LECO?
Yes, so coming up next month, it'll be my 15-year anniversary with LECO, entirely in the SEPSI division in research and development. And over my 15 years, I've worked on 3 of our products. I started on the TOF product, and then did some ion source development for the GC HRT product. And then starting in the spring of 2012, we launched the project called the Pegasus BT that replaced our Pegasus Classic instrument. And ever since then, that is the instrument that I've been working on. And now we're finishing up development on the 3rd generation of that instrument.
Very cool. When you think about the future of some of these mass spec products, is there any sort of material or electronic challenges that you think will have to be addressed to push the future forward?
So I think the answer is yes. For the BT specifically, there's always a push for better and better detection limits. You know, it's not always true, but there's a saying that I've heard that says sensitivity always wins.
Okay.
So if you have more sensitivity than your competition, you're more likely gonna win that competition, you know, when customers are looking at different systems. So pushing the BT to better and better detection limits, where we are now, where we can go. I think the limitation is actually the number of neutral analytes that we can turn into ions.
I see.
So if we can figure out ways to make that piece of the instrument more efficient is what will drive us to better detection limits in the future.
Very exciting. Crazy to think that the EI source is still really a main point of development and research.
It's tried and true, but there's always more things that you can do with it.
Understood. As highlighted earlier by Dave and now by Matt, excellence in source design will continue to be a driving factor in LECO mass spec innovations. With so many aspects of LECO mass specs having evolved, it is worth noting some characteristics that have persisted, most noteworthy among those being the lightning-fast acquisition rates. This is true independent of source type or mass analyzer, and speaks to LECO's true time-of-flight designs. Consider the mass spectral acquisition rates of various analyzer designs. Orbital mass analyzers top out in about the low tens of hertz, often suffering decreased resolution along the way. The best quadrupole and QTOF systems can usually achieve about 50 Hz with acceptable scanning windows. LECO's HRT and BT can achieve acquisition rates of 200 and 500 Hz respectively, without ever sacrificing full mass range acquisition. LECO does not pursue these rates as an arbitrary benchmark. Acquisition rates greater than 50 Hz are essential for GC by GC data collection and for achieving optimal deconvolution with fast chromatography, like can be achieved with hydrogen carrier gas or high-speed methods. I'll take a brief segue from mass spec to highlight GC by GC, or multi-dimensional chromatography. Just like regular GC, sample is injected. The primary column separates analytes in typical gas chromatography fashion. At this point, analytes go through a modulator, which quickly focuses bands and re-injects them into a short second column, providing a second dimension of separation. Critically, the first dimension of separation is retained, so instead of a one-dimensional chromatogram, you receive a two-dimensional contour plot. GC by GC alone can expand peak capacity tenfold in a chromatogram. This, in tandem with high-resolution information available in the HRT, can lead to exponentially rich data and runaway timelines for manually processing and comparing datasets. LECO realized that software innovations needed to keep pace with the hardware, and accordingly introduced ChromaTOF Tile, a tool for non-targeted dataset analysis. Tile reduces the processing time associated with rich GC by GC datasets by identifying chemical features and using simple Fisher ratios to determine significant differences between sample groups. The features of interest can then be assigned chemical identities based on their mass spectra and other information. And critical chemical differences between sample types can then be exposed with statistical tools like PCA plots. I sat down with Dr. Liz Humston-Fulmer to help me connect the dots between GC by GC, fast acquisition rates, and data processing tools.
Yeah, so I've been at LECO for 12 years and I work in our applications lab. I primarily work on our food, flavor, fragrance application projects, but I use all of our instruments, so GC, GCGC, time of flight, and all of our software tools as well.
Well, it seems like over the years, a unifying factor of LECO MS systems has always been lightning fast, full mass range acquisition. Can you tell us a little bit about how that feature can help in your application areas?
The fast acquisition rate really comes into play when you're talking about GCGC. So when we have multi-dimensional chromatography, we have very narrow peak widths. So having fast acquisition lets us sample those and get rich data for GCGC. Then having GCGC lets you explore even more complex samples and get more information about your samples.
Awesome.
Yeah, the full mass range acquisition is really helpful for any sort of non-target application. By having the full mass range, you're able to do all your library searching, you get good information about the analytes that you're detecting. So having the full mass range opens up options for your data analysis. So things like deconvolution are possible, and other peak finding capabilities are able to be used in our software. I think when you put all those pieces together, powerful hardware with powerful software, you really get to the best information that you can.
We at LECO hope that today's presentations and discussions evidence the strong tradition of innovation that brought us to the BT and HRT of today, and offered some insight into the exciting developments to expect from LECO in the coming years. Thanks for tuning in.